Good afternoon, everyone. Thanks for coming back for this technical seminar. So yesterday we discussed the relevance of precision physics for the collider phenomenology and why it is important to have theoretical precise predictions as well, up to the order of 1% uncertainty. And we also have seen what could be the state of the art methods in order to achieve such kind of precise theoretical predictions briefly. So today I will be mainly focusing on, like, with an example of my recent project, I will be talking about how we really do such kind of calculations. Okay, so just to recap a little bit on what we have discussed yesterday. So the standard model gives us the theoretical framework to describe the elementary particles, and we also saw that for in the last 50 years of measurement, we saw that all the measurements that we have at the colliders are pretty consistent with whatever is the standard model predictions. But we also have from the evidences that from other observations that there are something beyond the standard model, and we are looking for searches beyond the standard model from the collider physics as well. But in the last decade, after numerous searches, we could not find any direct evidences for new physics signals from the current experimental reach. So an indirect approach to probe such kind of new physics effect or the rare effects of this new physics program. Another things that we can do is the precision program, where we need both the precise measurements and also in order to catch such kind of rare events, we have to eliminate the background which is coming from the standard model predictions. So to explore such kind of precise measurements, we need the precise theoretical predictions from the standard model as well. And from the experiments already there are plans, well-defined plans, and which will be giving rise to, like, experimental error go down to 4 factor. So we need precise theoretical predictions to the order of in the same level. And we have also seen that from the theory, what we can control is the partonic cross section, and where the basic building block is the scattering amplitude, which we can use the perturbative methods in order to compute such kind of scattering amplitude, where we basically use the Feynman diagrammatic technique, where beyond the leading order contributions, we get virtual corrections and real emissions, which will give rise to loop integrals and phase space integrals. Okay, so beyond the next leading order become now a new standard, but beyond the next leading order, there are many challenges to do such kind of computations, and that depends on many factors, like which loop order that we are focusing, how many number of external particles are there, number of physical mass scales in the problem. So many things it depends on. So we have seen yesterday what could be the problems. There are, like, we have got that as we go higher in the loop and number of scale become higher, the number of Feynman diagrams and the integrals grows factorially, and that leads to complicated linear structure and integration that we have to reduce. That leads to large number of identities and complicated rational functions. And then with the internal mass in the problem, that even increase the complexity, because there are, like, non-rational functions in the problem. For example, the multi-valued square root kind of things will be appearing, which there are problems to do analytic continuations and things. And then solving such kind of higher order integrals also in terms of non-function is also not very straightforward. And then we have to handle the IR divergences as well in the problem. So these are the things that we have seen yesterday. So today let's see with an example, basically my recent work on light by light scattering. Let's see how we really do such kind of calculation. Okay, so let me first explain what I meant by light scattering. This process is actually one of the fundamental process. Yeah. If there is, like, more than we have an external mass, when it is internal, then we have terms which is not really square roots, branch cards and things like that. Yes. What? Yes. That as well. Logarithms as well as square roots. For the massless case, you are saying? No, if it is massless case, all the functions will be completely just polynomial, rational functions. Yes, but there is, okay. But logs that depends on just dimensionless parameters, right? that you can always write as a dimensionless parameters. But when mass comes, more branch cut comes in the problem. And what happens is that when mass comes, that I will talk later as well, you cannot, otherwise you can change your parameter and do rationalization so that your function become rational functions. But when it comes to mass, it is not always generalized. So yeah, this I will explain later on as well. Okay, so let's discuss with light by light scattering. So light by light scattering is nothing but how light interact with itself. So classically, such a process is not allowed. So there is no tree level diagram for light by light scattering. In the standard model, the first leading order correction starts from the 4 photon interaction through a fermion loop or a W boson loop. So as we can see that the leading order diagram itself are suppressed by order of alpha to the power 4. So it's a very suppressed process and very rare to detect at the colliders. But recently this process got revived the interest, because this light by light scattering is a sensitive channel to search for new physics. For example, if we have an axion like particles or graviton like particle that can interact with light photon like a tree level diagram, or there could be also beyond standard model particle come as or standard model extension comes as a loop diagrams that is interacting with the photons. So for this kind of new physics searches, one of the main background that comes is the standard model light by light kind of process. So it's important that we understand it precisely in order to look for such kind of searches at the colliders. Now another reason why it is again the interest has come up is because recently it has been observed in the LHC as well. Now I mentioned that when we look at the standard model Feynman diagrams, it is very suppressed at the order of alpha to the power 4. Still we observed that in the LHC because it's not really in the proton-proton collisions that we observed. We observed in the ultra-peripheral heavy ion collision. So LHC also, along with the proton-proton collision, LHC also have another program that is the heavy ion collisions. And it is not really a head-on collision, it's like a peripheral collision. And the ultra-peripheral means that the impact factor between them is really like more than the radius of both of these ions. So the ion here it is used is the lead ion. And what happens is that the cross section get enhanced because of the huge photon flux. So we know that along with the partonic cross section, we have to also convolute with the photon luminosity, photon flux, in order to really get the number that we can compute or measure with the compare with the collider measurements. And this photon flux depends on what is the charge of the heavy ion that we collide. For example, for the lead ion, the charge is 82. And the photon flux depends on z to the power 4. So it is basically 10 to the power 7 times more than whatever is the usual proton-proton collision. So this is the reason it has been observed recently in the ultra-peripheral heavy ion collision. So that is the reason now again this process got interest, and it would be nice to look at what is the theoretical corrections to that. Now earlier when they have measured, Atlas measured it in 2019. At that time only leading order corrections was available. And when we look at that, this superchick is the theoretical correction. Superchick is basically where they have taken the photon flux using a Monte Carlo generator, that is this superchick. So when they compare with the theory, it can be seen that the shape of the thing, the distribution is well reproduced, but except that in the first bin we can see there is a small tension. It's a very slight tension. It's like 2 sigma tension, so it's okay. But from the theoretical side, it is a motivation to check whether it is really due to some theoretical corrections. If we go to the higher order, from leading order to the next leading order, that is really the 2 loop corrections, because leading order is the loop induced process. So whether we take the 2 loop corrections, whether we can check whether that is coming from the theoretical enhancement or not. Monte Carlo generator to make the photon luminosity, compute the photon luminosity. Okay, so this was also another reason why we are interested in this process and to see what it will be giving. So what I meant is along with the leading order partonic cross section, we have the photon flux, and that photon flux is taken from the superchick. So they mentioned theoretical prediction superchick, that is the theory predictions. That's what I wanted to say. Not theory and theory. It is the theory is this red one, measurement is this one. So there is a yes. Yes, yes, yes. Yes, 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 yes. Yeah. So this is when Atlas has measured in 2019. But it's not really something that we need to worry because it's just 2 sigma. So if it is beyond 3 sigma or something, that we have to worry usually. But it is an academic motivation to see whether it's really to do with the theory corrections or not. It could be due to experimental statistical error as well. Okay. It's the invariant mass of the diphoton. Yes. Yeah, only it's mainly coming from, it's basically bottom quark. It's mainly coming from, yeah. Okay, so earlier also 2-loop computation has been done, but within an approximation. So there has been like considering massless limit, like fermion having massless, that is one of the limit people have computed. And another limit is in the low energy limit, where the energy scale in the problem is much less than the mass. So these are the 2 approximations that it has been computed. Our goal is to get the exact 2-loop corrections from that and how mass is affecting to the whole total 2-loop corrections. Okay. So to get that, our first aim is to get the scattering amplitude. So as I mentioned, this is like the wish list, what we want to get. Starting from the Feynman diagrammatic technique, we want to get a form that looks like it's a sum over some known special functions with the rational coefficients, provided that we know everything, the properties of such known functions. For example, if we take this known function as a log x, we know what are the properties, what are the identities this log has, and what could be the singularity or the branch cuts that logarithm has, and how we can expand them in a series expansion way, such that it has a fast numerical evaluation for the special functions. And for the rational coefficients, we would like to get something which is like very compact rational function, and we can manifest the cancellation of divergences from the analytic rational function itself. We can manifest the divergences cancellation, and also when we do numerical evaluation, it is like a well-behaved structure. So this is the wish list we want to try. Now, as I mentioned, this is one of the fundamental process and simple process. So it's not that, like yesterday what I meant, it's not that it gives rise to a very large coefficient that we cannot handle, but we would like to check with the available state of the art method, we can really find out a very compact structure that will be also useful for further formal studies. Okay, so we start with the how we can start the workflow. Because we have identical external photons, the possible scattering amplitudes structure, if we take all the tensor structure, total there will be 138 tensor structure is possible. But we can apply many symmetries because we have identical photons that we can apply the Bose symmetry to that. Then we can use the transversality of the photon, gauge symmetry. Applying all this symmetry, all these structures become 7 independent tensor. And that tensor looks like this way. This is the last tensor that we need to work out. Now from these tensor structures, we can construct a projectors such that by applying such projectors, the total Feynman diagram will look like scalar Feynman integrals and the rational coefficients. This we can always do by constructing projectors. So we are in this form where the number of integrals that we get is around 10,000. So that's what I meant, like it's not very large structure that we cannot really handle. So we have this 10,000 integrals. Now that depends on dimension as well as whatever is the external kinematics. Now the Feynman, projectors goes to each of the tensor structures. Yeah. And then you can actually write the amplitude as some scalar coefficient and the tensor structure. That's scalar coefficient is including coefficient as well as the integral. I meant the scalar way we can with the tensor structure. So once you calculated that scalar thing, then you got the amplitude, right? Because you know the tensor structure, how it looks like. This is a way to do it. Okay. To do it in a better way when we have, for a simple process, we can take projector as just the tree level diagram. But if the tree level diagrams are also more, usually people do with the projector techniques. And the Feynman integral has this form where basically the denominators are the propagators which are the linear function of loop momenta and the external momenta. Okay, as I mentioned yesterday, we can do the integration by parts identities, and from there we can reduce our 10,000 integral into master integrals. So we got 103 master integral in our problem. Okay, so now we are in this stage. So this rational function become complicated now. It's not the size of gigabytes, but it's like few hundred megabytes we have. At this step, we can really go ahead with, like, we have to compute the master integrals and we can just really get that, but we really want to get some compact structure that will be useful for further studies as well. So we try to get a compact structure from the for the rational coefficients, as well as we want to do the solving this master integral in terms of some special functions. So let's first see how we solve the master integrals. The method that we have used is using the differential equation method. So from whatever is our master integral, that 103 master integral, we can set up, like, this is the f is our master integral. We can set up a differential equation by taking the derivative with respect to the kinematic variable. Now yesterday I mentioned about this, that usually this differential equation is not straightforward to solve, but if we can choose a basis such a way that we can express this differential equation in a form like this. What I meant by like this is that, now this epsilon I did not say earlier, the epsilon is basically dimension parameter. Why we have introduced that? Because in the perturbative calculation we have divergences comes up, and how to regularize that is using dimensional regularization, where we introduce this parameter. Like dimension from 4 we change to a arbitrary dimension for minus to epsilon. That's how our amplitude now structure will also depends on the epsilon. So when I say dimension has been factorized, this is basically d minus 4 we want to factorize. So this we can always do depending on what is the kind of basis that we choose, basis integral we choose. So if we can write in this form, that the complete epsilon factorized form, where the matrix only depends on the external kinematics. Now why it becomes simpler? Because the integral here also we can always expand in terms of epsilon. Now together it will become like a totally epsilon factorized form. Then we can solve it order by order in epsilon. So where the first term, the epsilon, the leading term there, that will be, we can solve that using the boundary conditions available, and that result we can use to solve the next term. So this by order we can solve this in the epsilon. That is how we get the solution. Now we can see that the solutions looks like in terms of something called iterated integrals. These iterated integrals look like a form. I did not really give the form. It looks like a kind of many integrals of this form. Here this is one is a simple form, but usually it could be this C1. Yeah, the C1 could be any algebraic function. Yeah. Yeah. Yes. Yeah, it will be like in the kinematic invariance you have this T as well that depends on this scattering angle, right? So yeah, this information is there within, but during the calculation, yeah, we don't really care about the scattering angle. But once we get the numerical values at the differential level, probably. Yes. Yeah. So for the differential distribution, yes. I think you can extract that from that T. In the external kinematic variable, there is this T that depends on the scattering angle. Okay. So in order to solve these differential equations, you need to get one boundary term to solve it completely. For example, you can take the integral if there is a mass, for example. If the mass takes to infinity, if you can solve that term, with there is one scale has been down there, no? If you can solve that, you got a boundary term, and that will help us to solve the differential equations completely. Okay, to fix that boundary term, you have to actually know how the integral will look like. For example, this integral will depends on s, t and m square. Now you take m square goes to 0, whether the integral, you know the value of that, or m square goes to infinity, you know the value of that, you need. And some limit, yeah, that will act as the boundary term. Actually, I did not put an example, yeah. But I can actually later on talk to you with that thing. Okay, so in general, if we get an epsilon factorized form, we get a solution in terms of iterated integral. Now, this iterated integral we can express in different. It does not always happen. I mean, it's not even a general. It's also kind of what I can say. I don't know whether there is a mathematical theorem that shows that it can happen or not. It depends on your Feynman integrals as well. For example, what is that I meant? It actually needs this basis to be chosen in such a way that it comes out. But there are cases it will not happen as well. This is some simple cases as well, I would say, that we have 4 mass scales here. When the mass scales increases, complication increases, then you may not have this form. Yeah. Actually, I can talk about it later as well. There are something which I am not very familiar with, but yeah, that depends on how is your Feynman integral. As well as, yeah, you can do the in. So yes, you will get the explicit pole structure. Yes, exactly. Yeah, other epsilons actually comes from this series expansion, but yeah. Yeah. But when it comes out, it's like, so this is basically that you are asking the dimension could be the square as well. Epsilon power is coming from the master integral, that is true, but from the matrix you are asking, right? From the matrix itself, why the. Okay, yeah, you choose the basis integral in such a way that exactly. So you make all your basis integral to be. Yeah. And yeah. So no, that information is there in the master integrals. So this is only from the matrix form. Okay, there is a reason, but let me recollect. Here, this one epsilon dependence comes from both. Yes, that is there from both, and this has a series expansion like a with the pole structure to whatever it has. But in where I am saying that the A does not depend on the epsilon. From the A, from that matrix, we have completely taken out. Epsilon means it's basically d minus 4. And like, yeah, I cannot completely recollect. Exactly. So we choose the basis in such a way that it is, so if the pole structure is 1 by epsilon square, it starts with, then we choose a basis that starts with an epsilon square term so that it cancels. But why exactly, I need to just think about it. I don't recollect right now whether why it will not be an epsilon square. Yeah. Yeah. Okay. So this is the epsilon factorized form or canonical form, and we can get the solutions in terms of iterated integral. But if the case is like this matrix here contains only rational form, what I meant is that we can express this A in terms of like the form, it only contains some simple poles. It do not have any kind of square root or non-rational form. It contains only simple pole in that form. Then we can say it is in a form like a d-log. We can say this simple pole you can always write as a logarithmic terms, and this LK here, argument here is basically the functions of the external kinematics, which usually we call as the letters that will define the whole system. The unique singular terms in the Feynman integral is coming as the letters here. So if this A is in such a way that it is completely in a d-log form, then we can express this iterated integral in a much better form that is called multiple polylogarithm. It is a generalized form of polylogarithms, logs and dilogs, and then the generalized form is this multiple polylogarithms. In general, it can be expressed in this way, and this number of, so it is all these simple poles that is appears. And when there is n such integrals, then we can say the number of such integrations we can identify with a degree of transcendental weight. It also say the complexity of this problem as well. And we can say that once it is in epsilon factorized form, then each coefficient of this epsilon will have a uniform transcendentality weight. What I meant is that order of epsilon coefficient will only have a term with only one integral. Order of epsilon square will have terms like two such integral, weight 2, transcendental weight. So if we are working on two loop corrections, we will have to cancel all the, to get everything like until the finite term, we have to go until epsilon to the power 4. So the maximum transcendental weight will appear in our two loop computation is weight for transcendental weight, or weight for polynomial, weight for functions. What I meant, for example, I can say the rational number has weight 0, logarithm has weight 1, dilog has weight 2, like that. So we can say each coefficient of epsilon will have such kind of, they will keep that such kind of uniform transcendentality. Now once we can express in terms of these multiple polylogarithms, so this A tilde, if it is in this rational form, then the solutions of this master integral we can express in terms of these multiple polylogarithms. The multiple polylogarithms looks like this way, it's like a general form. It has many properties, and once it is written in this form, then we can say it is already well understood because we have libraries to evaluate them. So once we express them in terms of multiple polylogarithms, then we can just numerically evaluate that. So there are algorithms to do that. Now this is not always the case that this A contains only like simple poles or only rational terms. Especially when we have mass in the term, what happens is that there will be like square root, and that appears in the logarithms. And in that case, that is the non-rational form. In that case, we cannot really express them in terms of multiple polylogarithms. So such cases we need special treatment. So what we do in that cases, for us, our cases out of this these 103 integrals, which we can actually express as a 30 integrals and their crossing, out of that 5 integrals are in this form. When I say non-rationalizable square root, which basically means that the letter contains square root there. It is those square root, which basically 4 square root are there in total, and we cannot simultaneously rationalize them. By changing the parameter, we cannot do that. So we have to keep that square root there. In such cases, we cannot express as multiple polylogarithms, so we have to keep them as an iterated integrals, and we need a way to solve them numerically. But there are again algorithms to do that. How we can do is that, so the maximum it appears is the 4, as I mentioned, epsilon to the power 4, there will be transcendental weight 4 integrals will be there. The first weight 2 integral it is possible to express them in terms of logs and dilogs. What we have to worry about is the weight 3 and weight 4. Weight 3 will be just one dimensional integral other than these logs, so we can numerically evaluate them. And weight 4, we can use integration by parts identities again, and then make them as a one dimensional integral and do the numerical evaluation. So these kind of things, again there are algorithms to do that, to get to this structure, and we have a internal routine to do such kind of things, and this is how we treated such kind of 5 master integrals. And for each phase space region, we had to calculate them separately with boundary conditions has been calculated separately for each region. Okay, so this is how we have solved the master integral. Now, once we have that, we can express this amplitude in terms of this functional basis. What is the functional basis is basically the epsilon coefficient of this master integral we have. Now, we have already series expanded this epsilon, these master integrals. So, these are our functional basis, and in total we have 330 of them in our problem. At this stage, when we check, we have this large coefficients which is of like around few hundred megabytes, and then we cannot see analytic pole cancellation. We can check that to a different phase space point and see that it is converging to 0, but we cannot really see that like manifested this by from the analytic expression itself, that we cannot see. And there are some regions where we can get, like, because this coefficient could be larger, there can be numerical instabilities in some regions. So we wanted to actually check whether we can really make the whole thing to make it compact. Now we have done some procedure to do that. One of the thing is to look for whether there is some relation. We can use this functional basis, now it is an iterated integral form, or we can use the properties or multiple polylogarithms. So we can use the properties of these multiple polylogarithms or iterated integrals, and to find out whether there are relations between this functional basis. That is the first step we have done. What I meant here is that at the order of epsilon 0, we have only rational numbers. Epsilon 1, we will have something which is of weight 1 integral. Epsilon 2, we will have weight 2 integral, that is pure weight 2, or it could be like a weight 1 square kind of integral. Similarly, at weight 3, we can have something like this. It could be weight 2 or weight 1, or it could be weight 1 cube. This kind of integrals will be there. So here UV divergences will be there. So this is not like we can actually give the renormalization together, and then we can check in the phase space each different STU values. We can apply that and see whether it is going to very small number. This we can check, but it is not explicitly there that there are coefficient for the 1 by epsilon square and 1 by epsilon as well. It's not. We can check that whether it is going to 0 numerically, but it was not analytically. It was not there. Does that make sense? Yeah. When you add the renormalization, counter term, yes. So we checked at this step, adding the counter term, whether we really get the pole cancellation or not. At this step itself, we checked, and it was not. I mean, it is there in different phase space region, but not explicitly in the analytic function. So that is the reason, and then we have methods also that we can apply so that we can make it fully compact. So that's why we really go on with the procedure. So what one can see is that, for example, in the weight 1 integrals, there are different weight 1 functions we can have. Then we can see whether there is a linear relations between them. If it is there, then we can choose one over the other, and from one of them we can get the other one. It's similar as the integration by parts, the linear relation to get this IPPs also we were doing the similar thing. So such a kind of elimination we can do here as well. Similarly, for the weight 2, we can try some of the weight 2 can be expressed in terms of weight 1 integral. This is always possible because there are properties for these multiple polylogarithms and iterated integrals that satisfy this shuffle algebra and some linear algebraic functions. So we can check whether such kind of relation exists for the weight 2 integral in terms of weight 1 with power squared ones as well. And that systematically we could check, and then we could reduce, and we can only take the independent weight 2 integrals, and all of them we can express them as weight 1, which we eliminated because we can find those relations and then apply that. So if there is some kind of these relations are there, then we choose the weight 1 integral instead of the weight 2. So such kind of elimination we have done. We prefer the lower weight functions over the higher weight, and if the 2 loop functional basis can be expressed in terms of 1 loop functions, then we prefer the 1 loop over the 2 loop. In such a way, we could take only the independent and irreducible functional basis for this total one. And then not only that, we have also checked whether there is some kind of symmetry relations between these functional bases. For example, there is some kind of crossing symmetry between different functional bases, and that could be also we could find out. And in total, from the 330, we could reduce down to 84 independent functional bases. Similarly, we done the similar thing for the rational function, as yesterday when what I mentioned. Because the rational function is huge, just working with that is not really giving us the compact structure. So it is better we apply everything using a finite flow algorithm. So what we have done is that once we get the scalar kind of form, that rational coefficients and then scalar Feynman integral, this we give as an input to a finite field algorithm. We apply integration by parts numerically over different sampling, and then what we get as the IPP reduction is with coefficient, that is numbers, pure numbers. And then we can apply the epsilon expansion also within that algorithm. Then it will become like this way. Then we can also apply all the relation that we found between these functional bases, that also we can apply. And finally, the last coefficient we can try to reconstruct them using the rational reconstruction algorithm. That is also within this algorithm, it has been provided. So by doing this thing completely using finite field techniques, we can bypass the intermediate large expression. Okay, so this has changed. Before that, if we don't do with the finite field technique, to do such kind of thing, it takes a few days to complete the things. But once using this, it could be reduced down to 1 hour for the one loop. But before that, we have to check all these relations and everything. That took time, but once everything is done, we can see that it has come down to 1 hour. So this is the peculiarity of using finite field technique, how much it is useful. Now there are, as I mentioned, there are algorithms which has been already implemented. Main one of them are the finite flow and Firefly. For this project, we have used finite flow in order to do such kind of algorithm. Yes, yes, yes. Yeah, 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 yeah. Sorry. Actually, the prime is not, yeah. Why I am unable to tell you in an explanation, because the prime is not actually chosen by me. By looking at the expression, the prime is chosen by the algorithm itself. They choose in such a way that it is it's like a 32-bit or 64-bit kind of number, and so that it can actually over many primes, it can actually evaluate the whole rational functions and get it can reconstruct back what could be the symbolic form. But I will come to you and probably we can discuss more. Yes. Okay, so once we got everything, so we got this way. So this is, it's really what it means is that there is rational coefficients and there is 84 independent functional bases. Now after this step also we have done a little more work, that is finding these rational coefficients, whether they have any kind of linear relations. That we can always do by solving a linear fit problems and then try to find out whether there could be some relations between them. This also we tried. And then that actually changed down to 30 rational functions and their crossings. So together the whole procedure I just summarized here, starting from the 10,000 integral, by doing IBP we got really 30 integrals, total 103 master integral, which we can express as a 30 integrals and their crossing. And this master integral in the uniform transcendental basis at different weight, we got more than 300 master integral. Using the relations between these functional bases, we could make them 84 master integrals, functional basis. And the rational coefficients also we apply these linear fit problems and we could write them in terms of 31 and then crossings. Finally, the whole thing we could really write down in our paper. So usually a 2-to-2 process with an internal mass, it's so complicated that you can really just give a numerical behavior of that. But in this project, we really try to write down in the paper such that it will be also useful for further studies like checking different limits and things like that way. Okay, so now we have seen how the calculation has been done. Now let us see the phenomenological relevance. Yesterday I have told about it a bit. Today let's discuss a little more. So this is the partonic level, like if we don't take care of the photon luminosity, how it looks like, whatever is we calculate right now, how the behavior looks like. So here the red and green line actually shows the previous approximation in the high energy limit, that is shown in the red, and the approximation in the low energy limit. What we can see is that this approximation really behave like a constant kind of behavior, but the exact result has a non-trivial behavior that could not be guessed by from these low energy approximations. Now we have also checked with photon luminosity, incorporating the photon luminosity here, we can really check with the measurements. There also we can see that the high energy and low energy expansion, how the nonlinear behavior that we get for the non-trivial behavior we get for the exact results. Now, earlier I told about this, what was one of the motivation was looking at what happens at the lowest beam. Here we can see that it has this tension between theory and measurement has been reduced, but it's not really eliminated when we check from the atlas measurements. But after this, CMS also observed this light by light scattering, and from their things it could be seen that actually the behavior looks like within the uncertainty they are matching with the theory. So it seems like it could be from the statistical uncertainty of the measurements, but this needs to be proved from the upcoming measurements and seen that whether those kind of tension is really there, and if it is there, how we can eliminate that. So CMS result has been, yeah. Not really from the leading order. I mean, they have taken our result, but our result, the enhancement is like 6%. So it is not just the theoretical uncertainty. It could be also because of the statistical uncertainty. So now that it is agreeing with the theory result, they could make more constraint to the coupling of the axion-like coupling with the photon, and also for the graviton-like particle coupling. And this is the most stringent constraint they could make it. And this statistical uncertainty right now for the CMS is around 30%, and by the high luminosity LHC they are aiming towards to get within the 4%, and there probably the theoretical uncertainty become more relevant, and we need to see, yeah. Just from the running of the coupling constant. That Alice, Atlas. Actually, I am not really aware about this alpha S coupling at the CMS, how it is. Yeah, I don't know. Okay, so I hope a real calculation has convinced about the methods and how the phenomenological relevance is coming up. Now, yeah. Yes. Actually, the thing it ruled out this region. So now CMS has whatever is this red one, which is better than whatever was the earlier one. So it has again many regions to rule out, but it actually ruled out these regions basically. Yeah. This one. So the gray is the whole ruled out regions. Yeah. I mean, we don't know yet. I mean, yeah. I mean, right now it is allowed. Yes, exactly. Yes, but right now I did not put that one, but I think so. Actually, yeah. They have studies with the graviton particle as well. Probably Josna can tell more about it. Huh? Yeah, but this one is really for the axion-like particles. Yeah, for okay. So, yeah. Wait. Can we have a scalar? Just scalar with a. So what? Yeah, from that is using that is using some other. This we can do with. Okay. So let us see another kind of accuracy, that is the logarithmic accuracy. So until now I have talked about the fixed order kind of computation, where we have the perturbative series in the order of coupling, strong coupling constant. Now let's see how we can do the precision with the logarithmic accuracy. So I will just briefly talk about that. As I mentioned yesterday, this perturbative series has infrared divergences, but when we add up both virtual and the real emissions, that become IR finite. But what we can say is that in certain phase space region, these finite terms contains logarithms. That logarithms, one of the such region is the threshold region. What I meant by threshold region here is that, for example, if you have a Higgs boson protection, the threshold region is when the mass of the Higgs is very, very close to whatever is the partonic center of mass energy. So that is when q square by s hat is very, very close to 1. In that time, this logarithmic term log 1 minus q square by s hat will be very large, such that it can overcome the coupling, the suppression by the alpha s, or we can say that alpha s L is order 1. So that means that we cannot, perturbative coefficients could be unreliable. So in order to take care of such kind of region, what we can do is that there is a procedure called resummation. Now this has been studied. This is like we know now what could be the logarithmic, how the logarithmic term behaves like. For example, in the partonic cross section, we can see that the threshold logarithmic structure looks like this way, that each order in the coupling constant, the leading logarithmic terms looks like L to the power 2n. This can be studied by actually the threshold limit. There is a factorization where we can factorize the partonic cross section in terms of the hard region, soft region and collinear region, and each of that satisfies some kind of RG evolution equation, and there is IR factorization as well, and from there we can actually reach to this point that how the behavior of this logarithmic looks like. There are many works and many studies along that direction. So let's take that this is how it looks like. Yeah. After, yes. The singular part got cancelled, but this log terms will be there. And that log terms are also okay, but in the special regions, there are different such regions where you have to take care of such kind of terms. Now, when we look at this partonic cross section, the log terms here, if we apply the log term, how it will be looking like. What we can see is that when we look at the leading logarithmic behavior to the all order, like whatever is the available order that we can see, and also we can prove that to the all order, what we can see is that all this information depends on just the first NLO information, like whatever is information we have from the next leading order calculation, only that it depends. It is basically the RG evolution it goes on until to the whole series. So there is a kind of exponential behavior that we can really take a resummed series. Similarly, the subleading logarithmic term also we can see that it depends only on the next leading order. So this kind of behavior it shows. So we can express the series in terms, instead of this one, we can express the series in this way, where our coupling is, instead of alpha s, the coupling is alpha s L. And whatever is the coefficient here looks, it is actually kind of all order information. All order information not for the all terms, but for the leading log terms, this contains the all order information. If we have the next term, that means it has the all order terms of next leading logarithmic information. So like that way, we can actually write a resummation to that. And we say, if we have this term, we say that it's the leading logarithmic accuracy or next leading logarithmic accuracy, similar to whatever the fixed order corrections. Now what happens if we have this kind of way? First of all, it gives better physical description, but not only that, it also carries certain information from the higher order. And sometimes in this phase, some of the phase space region, because of this large logarithm, this contribution become the dominant contribution. So by doing this, we get some dominant contribution from the higher order without doing all such bigger calculation, because resummation is actually coming from the RG evolution and then infrared factorization, and we can really solve them without doing all such kind of big computations. So by doing that, even though we don't have, for example, if we don't have N3LO computation for a process, if we can do a resummed correction, that actually contains some information from the third order. So this we can already see that how the scale uncertainty reduces for this kind of things. That with an example, let me show that. Yeah. For the up to like what I can say, for this kind of behavior like alpha s to the power, for this kind of term alpha s to the power to L to n, this is called leading power. For that it is proved that it is exponentiated. But there are next leading order power where instead of this kind of term it will be like so this is like what I can say, sorry, yeah, so this actually this term will be looking like log 1 minus z divided by 1 minus z. It's a kind of plus distribution it will be looking like, and those kind of thing we say leading power. But there are other terms, there are terms like just log 1 minus q square by s hat, and there it's not yet proven that this exponentiate, that studies are still ongoing, which is called next leading power resummation, and there only we can see that only leading logarithm we can see something, but beyond that people argue that there is a kind of factorization is broken there and we cannot really exponentiate and things like that, but studies are ongoing there about that. Yes. Yes, yes. Yes. Yes, yes, yes. Yes, here also it is the similar way. But what I meant is that when I say this kind of way, actually some details I am not saying. What I meant is that the leading behavior is it's log 1 minus q square by s hat divided by 1 minus q square by s hat. That is how the term really. So q square by s hat, if I say z, the behavior is like log 1 minus z by 1 minus z, that kind of things. Now the next term in the series will be just log 1 minus z, and that is really collinear behavior, and it could not be yet proven that it exponentiate. That studies are still ongoing. In the higher term, yeah, no, yeah, no, yeah. No, not higher order in this sense. Okay, higher order in the how, yeah. For example, what I meant is that when we really do the partonic cross section, the behavior looks like, first term looks like this, okay, but there are next term that look like that is like subdominant. This will be the dominant, like most dominant one, most singular, exponentiate, exponentiate like for the leading log, for the next leading log. So this is the leading log term. Next leading term is basically this term will be the next leading log, like that. Similarly, you can get this is the leading log. Similarly, there are, that is called next leading power terms, and such kind of things we don't yet have this kind of a generalization. Yeah. Now, when we include these terms, what we can see is that, for example, I compare the fixed order correction here, and this is the resum. We added, along with the fixed order, we added the resummed also here. Okay, so this is NLO and NNLO and 3LO and NLL, NNL and 3LL. What we can see is that when we include the NLL, for example, it really, we can actually see that compared to the NLO, it actually has some information from the NNLO, because the central value is more closer that we can see. From the fixed resummation, it is just the information from the next leading log, but it contains some part, the logarithmic correction from the all order. That is why it is actually very close to whatever is the NNLO. Similarly, when we look at the NNLL, we can see from the fixed order whatever is the higher power, that is the N3LO, that central value is very close to whatever is the NNLL. So this means that, for example, this is the N3LL. We can say that N3LL is already like convergent towards the NNLL, which also could be, we could say from that, probably the N4LO result is already perturbably converged. So it is really close to somewhere here. Which means that when we include the higher order in the resummation, at least in some cases, it actually carries information from the higher order. So even though we don't have n for LO computation, from the leading logarithmic behavior, the n3LL behavior, we can have some information from the n4LO, from the higher order corrections. Now this is for the di-Higgs case, we have done these resummed corrections, and we could see that the uncertainty from the theory, there are many different various uncertainty, but from the scale uncertainty it has been reduced down to percentage level uncertainty. But of course for this process, it is a very complicated process, and it could not be possible to do this to next leading order corrections yet. So only approximations are there, and there are many uncertainty from different sources like scale and missing higher order and quark mass key, and many uncertainties are there. From the scale side, we could reduce down to percent level, but there are bigger uncertainty coming from the other part which needs to be taken care. Okay, so let me just briefly give just 2 minutes I will take, just the research plan that I would like to do. So subtraction method, yesterday I mentioned about that. So these subtraction methods are required because we can see that real and virtual corrections become finite, but it is to implement that case, it is really hard to do that beyond the simple process. That is because these real emission corrections are much complicated, and we have to also study different phase space regions, which needs to be having numerical phase space, numerically evaluating these phase space integrals, and before that we have to really eliminate the divergences coming from the real emission. So what we can, the idea is very simple. What we can do is that if we can construct a subtraction term such that it has the same behavior as the real emission, only in the limit where the singularity comes up. Like the singularity comes up in the soft limit and the collinear limit, yesterday we discussed. So how the real emission looks like in the singular limit, it should behave in the similar way, but it should be very simple enough that we can actually do analytic integration. If we can construct such kind of subtraction term, then we can actually apply eliminate such kind of terms from the real emission, so that this integral is finite, and we can numerically integration can be possible in 4 dimension. And what we have to do extra is just that this we have to analytically integrate out, but because it's a subtraction term is much simpler than compared to the real emission, this is possible. Now constructing such kind of subtraction term is not really generalized. Of course, at the next leading order it's completely known, and there are very well known algorithms to do that, and this known as FKS and dipole subtraction methods. At the next leading order there is tools to do that, but at the next leading order this kind of generalization is still getting studied. There are different kind of methods to do such kind of subtraction, but none of them are like fully complete. So there is no general method yet for any processes that need a good understanding on the infrastructure of QCD, and this is one of my interesting part that I would like to do. So I have already some experience on that, working on FK subtraction for the quark Corning protections, and at the moment I am also looking at the next leading order correction using nested soft collinear. So yeah, this is one of my plan to continue to doing. And I also, along the fixed order direction, I have also plans to look for electroweak corrections where things become much complicated. But once we have N and LO in the QCD, just by power counting we can see that electroweak coupling also become like NLO electroweak also become like, we have to take care of that, because in some phase space regions it given that around 10% of enhancement. So it's good that we can take care of the electroweak corrections, and right now the ongoing research is going on the electroweak corrections and also 2 to 3 scattering process. So these are some of the things that I would like to do. So that comes to my conclusion. Just to summarize that my main research interest is based on precision calculations within the standard model using perturbative methods, and here I wanted to convey 2 such kind of methods that where we can improve the precision using fixed order corrections and the resummation techniques. And we can see that one of the things like light by light scattering, academic interest is also there, how we can really use the state of the art methods to get to a very compact structure, that is numerically evolution is also possible. And phenomenologically also we can see that this is actually a window to new physics. So our result was also useful to get the constraint on the new physics particles. And the resummation also we can see that gives a better theory description, and also because it involves a higher order information, it gives some part of the information from the higher order. So when the fixed order corrections are not accessible, this is one of the way that we can approximate the results to the higher order. So thanks for the attention. Yeah. Yes, actually what we have computed is the helicity amplitude, where we actually give what are the all possible polarization states. All. Yeah, we have to add, yeah. Then we finally add up everything together, but yes, 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 yes. Yeah, so some of the checks we can do, for example, whether all the pole cancellations are there, and then, yeah. No. So our usually the two loop correction have, um, so we need to have until epsilon to the power 4 that will give rise to the finite contributions. So okay, this epsilon is basically the dimensional regulator, right? So it will appear as 1 by epsilon square term is the pole structure. That should cancel when you do the, okay, then finite term is just epsilon 0 term. So you don't need to put any value to the epsilon. All the pole will cancel and the finite term is your amplitude basically. Does that make sense to you? Yeah. Yes. Uh-huh. 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 Yes. Yes. Yeah, I got you. Yeah. I mean, you don't need to even put the epsilon equal to 0 in the higher order. Yeah. Yeah. Which region the resummation is? Sorry. Okay, resummation. Okay. It that subtraction is basically really taking care of only that singularity term. Uh, so, sorry, this is what. So, yeah. Ah. Ah. Hmm. Yes, yes, yes. But actually, I don't know about this method. Yeah. Yes, 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 yes. Yeah. Yes. Yes, yes, yes. Yeah. I was thinking to check this, I forgot. But this is also actually one of the main background for the axion-like particle. This is also one of the main background. But I think it is already available because that for sure, yeah, because it is a tree level that vertex. Yeah, I will look that and tell you. Okay, thank you very much.